So my name is Nicolas Pitre. I've been working for Linaro since the beginning. For the last 2 years, I've worked on this project trying to shrink the Linux kernel so it can be suitable for IoT purposes. Someone said in the previous presentation that Zephyr is there where Linux can go, but my goal is to push Linux downwards where Zephyr is right now. So, as you probably know, I am blind, so if you have questions or remarks, please don't raise your hand, just speak up, otherwise I won't notice you. Okay, so slide number 3. I do have only half an hour for this material, so I'll go fast because otherwise I could talk about it for more than an hour. So slide number 3, IoT goals. Of course, we want to have low cost, ubiquity, and everything that we can have for IoT purposes. It has to be cheap, it has to be secure. So slides 4, solutions. You probably already know all about this. We have to avoid custom solutions, work around the common infrastructure, and so on. Slide number 5, please. So Linux is probably one of the best common piece of code out there. So if we can leverage Linux for IoT purposes, we're going to have all those nice features that Linux carries, which is a lot of developers, a good network stack, and Linux is already widely used into embedded setups and so on. Slide number 6. Problem with Linux, it's big. As people have noticed, it cannot work with systems with a really small memory. It is tuned for very high-end systems, and usually it scales up more than it scales down. Okay. Slides number 7. There are automatic techniques to reduce the Linux kernel. We can have the linker discard sections that are not being used. We can use LTO, which is a link time optimization that GCC provides, or manual techniques, which including more configuration options to remove pieces that are not used, or re-implement part of the code into a smaller format. Slide number 8. This is an example of subsystem trimming that have been already implemented in the kernel. So we can remove printk, can remove NTP support, and so on. Slide number 9. So one of the things I did since my last presentation is to introduce more options to remove some of the part of the kernel, which is, for example, removing the Posix timers. Most of the time in some embedded setups, we don't have a need for the full spec of the Posix timers. So removing them, it reduces the whole time subsystem of a reduction of 28%, which is not that bad for something that we don't use, right? This is available in kernel 4.10. Slides number 10, please. I also submitted some patches to remove the PI futexes. So if you don't need priority inversion, priority inheritance support in your kernel, if you don't have the real-time mutex support in your kernel, you cannot have the PI futexes. So now it's possible to have simple futex without the PI support. it provides a 51% size reduction on that piece of code. This has been merged into the latest kernel. Slides number 11. Another thing I worked on is to reduce the size of the scheduler. I hinted about that the last time I presented this. It provides a really nice size reduction of the scheduler. Thing is, the chances for those things to be merged upstream are very slim. So, I took another approach, slide number 12, is to use the existing scheduler code and remove part of it. For example, the deadline class scheduler is rarely needed in embedded setups. So I managed for the scheduler to be able to configure that part out. It is much less intrusive, and the preliminary work has been merged already in the kernel. Slide number 13. Same thing can be done for the real-time class. So with those two things being combined, you can have a nice reduction of the scheduler size. It's not as small as the tiny scheduler implementation I did, but the thing is, if it can be merged upstream, there's more chance that people will use it and maintain it than if it's kept outside. Slide 14. Even then, had some problem with upstream maintainers, right? So basically what Ingo Molnar told me is, if I cannot demonstrate this into a real product, there is no point merging all this into mainline. Which makes kind of sense, of course. So I decided that I needed to have something that runs onto real hardware, real target hardware. So slide 15. I chose a target hardware platform, which is the STM32F469 Disco board. It comes with, it's a pretty beefy board already. It has a lot of RAM and flash that can run Linux already. So what's the point? Slide 16. The ultimate goal is to be able to run Linux on this single microcontroller alone. It has a tiny amount of SRAM built into the chip. So if that can accommodate Linux, then we could have a really nice target for this project. Slide 17. Of course, I needed to have a change of strategy here. When we talk about shrinking the kernel, most people think about the code size. Thing is, this microcontroller has quite a large amount of flash memory, but a tiny amount of RAM. So the idea is to put as much code or read-only data into flash and focus on the reduction of read-write data usage. So to do this, slide 18. First thing, Kernel Xip. This is great because that work has already been done before. The thing that I added to it is to compress the data segment that is going to be copied into RAM anyway, but store it compressed into flash. So the flash space is more, there's more flash memory available for other things afterwards. Slide 19. User space XIP. If we want to reduce RAM usage, we need to be concerned about user space as well. So to be able to run user space from flash into a system with no MMU, we have to look at some file format that are able to split the text segment and the data segment so that text segment can be run from flash and not be tied with the data segment. So on the new MMU support for Linux, there are two file formats that can be used. The BFLT, which is the legacy UC Linux format that's been developed. Thing is, it's pretty badly documented. The tools to deal with it are kind of hard to work with, especially if we want to have separate data and text segment. The other file format is the FDPIC for ELF. That format is really nice because it has been designed from the start to deal with separate text and data segment. It can be processed with standard tools. It can be inspected with the bin utils without any modifications. So that's what I used, and I really thank the ST guys who worked on this, so I could use their patches, and I just made them suitable for mainline upstreaming. So apparently, this is going to be merged into mainline for the next merge window. Slide number 20. For user space XIP to be possible, we need to have a special file system as well. So I settled on the CRAMF because it's simple. It uses very little memory. And there used to be a patch set back in the days that made it possible to use a user space XIP with it. I dusted them off and ended up rewriting them because I wanted those patches to be upstreamable. So I made XIP work with no MMU and MMU version of Linux if you use those patches. Okay, slide 21. Back to the kernel. The kernel itself has some kind of memory footprint. Its data segment is copied to RAM, so we need to look at it and reduce it as much as possible. The default kernel I have, it started with 80K of data usage and 54K of BSS usage. So slide 22. I write a script to find out what those symbols were. So the idea is to take the system.map file and just subtract the address of one symbol from the previous one to get its size. The result of that is on slide 23. We can see that the biggest variable there is the log buffer, which is the print key. That's easy to reduce because there's already configure options to decide the size of this. But there are other things like the timer infrastructure, the work queue, and so on that are taking more space. If we look at slide 24, there are things like the thread size, which is the size of the stack of every process in the kernel. The first one is the init process. It uses the BSS segment. So if we put only one page for each stack, that reduces BSS, and things afterward that we'll see later. And various hash tables that have parameters to decide their sizes. Those things are pretty arbitrary, so we can modify those to put very small tables instead of big tables, especially if we have little memory in the system. We don't need to have big tables. Slide 25. Result. I obtained with simple tweaks a 28% reduction in the static footprint of the kernel, which is pretty nice already. Okay, slide 26. So let's boot this thing. First thing we can see is that the kernel is using 32 pages of RAM just to track memory pages in the system. So, of course, I was using this Disco board, which has 16 megabytes of RAM. With that amount of RAM, we, of course, require a big memmap array to represent all the memory. So that's easy to solve. We just reduce the amount of memory that the kernel can see. There's another thing that is not tracked here, and after some digging, I discovered that the unflattened device tree occupies something like 13 pages. I didn't talk much to the device tree people yet, but what the heck is in those 13 pages for a system that small? If this data could be stored into flash instead of RAM, because otherwise RAM is, I will have to verify with the device tree people, is this data being modified after boot or not? If there's a way to store this into flash instead of RAM, we're going to save space for the things here as well. Okay, that's static RAM. Slide 27. Then there are some tweaks to reduce the dynamic memory allocation on the kernel. For example, the work queue are allocating per CPU memory as well. There's the per CPU allocator. We still have only one CPU, of course, but the pure CPU allocator is there. I did some changes to do so it reserves only 1 page of memory instead of 8 by default. By reducing the amount of memory that the kernel can see, the memmap array shrinks from 32 pages to only 2 pages. Slide 28. What about the init calls? It could be a good idea to track what each init call is using in terms of amount of memory there. So slide 29. We can see the list here of memory usage by page for each system calls. Do you see a flare there? Again, it has the OF prefix. I guess I have to talk to the same people once again. Slide 30. So from user space, once it's booted, we can inspect proc info and so on to see what the memory representation is. One thing which is interesting here is that memory dedicated to user space is only 84K. And here I'm running a shell and the cat process that displays the information there. So slide 31. So that's about the memory distribution that I could figure out so far. There's about 140K of device tree data there. This is probably the biggest memory user so far. And things don't balance. There is still memory that I didn't manage to track so far. But still, if we think about the previous goal that I wanted to run Linux onto that microcontroller, right now it is running into 800K of RAM. I would like to lower this to maybe 512, but I've been told by the some ST guy that they do have a version of their microcontroller that has 1 megabyte of static RAM in it. So if we take that particular microcontroller, the goal has been achieved already. So slide 32. It's much easier to shrink data usage than code size. That's one thing I realized. So the solution that I have here is still incomplete. There's still some work to do. Need to find some strategies for device tree support, maybe see what's been done with device tree in Zephyr. And now, if we have time, do we have time? 8 minutes. I do have a board. I can show you, can boot it in front of this crowd. Once again, if someone could display this on the screen. Yeah, it's only a USB cable.
You got a USB? Just this. So that goes in the power pack, yeah?
Yeah, it's power and
but
serial port.
But your power here. Any USB slot? Just this one? There you go.
Okay, no, but I mean, it needs to be connected to a laptop that can.
Oh, okay. Sorry.
Can display.
Hang on to that, just a sec. I'll go get my laptop.
Bring it with you.
Yeah, I'll bring it.
I mean, the board.
Yeah. Yeah.
Yeah. So you have a terminal emulator?
We'll find out in a minute. So, quick question, Nicolas. You're basically looking at everywhere you can take some pages out of the system because you don't need that amount of stack. But I mean, there's, you keep going. Do you have any idea how much smaller you can make it using this technique? There's a law of diminishing return.
Yeah, it probably depends of where the memory in track yet is. For example, device tree is a big chunk of memory. There is still some memory unaccounted for, so I need to find out where that is. For example, there's a long stream of very small BSS allocations from the kernel, and while I was able to tweak those for the large hash tables, the long stream of very small allocation, like 4 bytes allocation all over the place, those are much harder to remove because it's a lot of things. And one thing I noticed as well is that even though I used LTO to reduce the kernel size, once the kernel is that small, at some point there is not much else to remove. And even if the code is being optimized by LTO, it doesn't reduce the amount of data usage that much. So it's really about finding where the rest of the memory data
Yeah, so it's like a big treasure hunt.
But if eventually, if we have Linux running into 640K of RAM, someone said at some point that it would have to be enough for everybody, right?
We'll do it separately. I think you need a separate demo.
Yeah.
I have a couple of questions. First, all the stuff you presented here, is this in your tree or no?
Most of what I presented is in my tree. Most of it is destined to be submitted upstream. There are some pretty nice hacks that I didn't publish.
Okay.
Like just overwriting constants in the kernel, that those are hard-coded at the moment. They need to be selectable somehow.
And the other question is a more long-term issue. What's your concern about you doing this to shrink it and another 10,000 developers not worrying about it and kind of at every release potentially growing it back up with their changes?
Well, I think it's a question of awareness. Right now, most developers, they just don't care because they don't see the need. So that's why, to convince the upstream maintainers as well, I wanted to have a target that I can show that I can run Linux into that small amount of memory. So at that point, it becomes awareness of the usefulness of this thing. And afterwards, we can have automatic scripts that will just look for size regressions and so on.
Sorry, Nicolas, I think it's with only Nico guarding the ball, that's quite hard. But the more people that get involved, it will become something that people are all aware of.
Yeah. And if people find this useful and they can see value in this, then eventually I won't be alone working on this, and probably will help.
Nico, your work is mostly about the kernel code. What C library, and I presume it's BusyBox that you're using?
Yeah, it's straight BusyBox. Didn't modify it at all.
What's the C library?
Sorry?
Which is the C library?
115, 200. And then you need to press the reset button to reboot it. Do you got it? So sorry, I interrupted you.
It's 80. We got some double guys right now. Hang on a second.
So to answer your question about user space, the only thing I did is to limit the stack size that Linux allocates to user space processes. Because
And which user's C library are you using?
it's the, I think it's UC libc. It is working? So you have a shell, you can do ls, you can wander around and just try free. one thing which is really funny is that the kernel will display some sizes of every part of the kernel when it boots, and it rounds it to the megabyte. So some things are 0 megabytes. So it works.
Yeah, it's showing just having a little look around.
Yay. Any more questions? So I think we're done.